Connected Components Workbench, industrial automation software, and we are specifically discussing the lab projects for this on training manuals. The videos right now are online. Right now they're free on YouTube, but they will not remain free on YouTube indefinitely. But for right now they're free. Specifically, what we want to talk about first is the hardware that we're using to make these videos, and then talk about some data types. So this particular video is not a lab project, it's just a discussion in the middle. So the hardware that we're using, you see 4 controllers in front of you. The small one, if you like, in the lower right, that's a Micro810, and you see attached to it a little box that kind of sticks up with an orange USB connector. Now this is a product that we actually sell on the website, and we sell them only in case people don't want to build their own, but you're, I think, better off building your own because you get the experience then of soldering and assembly and really a better understanding of the electronics and the electrical. So that Micro810 is what I used to do a lot of these projects when I was developing the manual. Then at some point I switched to an LC70. Now the LC70 is at the top of the family tree for the Micro800 family, and the 810 is at the bottom. So the one that you see mounted on the box there in the lower right that has 6 toggle switches and 4 lights, 2 of which are actually push buttons as well. That's the bottom of the family, and then all the way over to the left, that's the 870, the Micro870. Now then I have mounted on a box with, it looks like 8 toggle switches, and you can't see them all, but 8 LED indicators, some of which are also push buttons that are interconnected with the toggle switches on the leading edge of that box. Now we don't sell this product. This was just a prototype. I decided against it, but it was built, so that's what I use when I am developing a lab within 870. Back over to the right on the bottom is that 810. Right above it is an 820 that has the remote LCD mounted below it. The 810 at the bottom on the right has USB only, and you have to make sure you buy that USB adapter that's plugged in there. That little screen does not come with it as well. Those are all separate purchases. Right above it to the right is the LC20. So the 820, the Micro820, you see a processor and then a couple slot covers. So we have no extra I/O modules mounted in this 820. And then on the processor you see, it looks like a black, yellow, and blue wire. Those run down to the bottom of that remote LCD. That is RS-232, so that connects the processor and this HMI via RS-232. And then on the front of this remote LCD you see a little white cap. If you pop that open, that's the USB port. So I did this so I would have a USB port to that processor. I'm not really doing a whole lot right now with that HMI, but that's the primary path to get a USB connector to an 820. And the 820 also has Ethernet, which you cannot see the port, it's on the other side. The 820 in the upper right is connected with a digital field device simulator that has 6 toggles and 6 LED lit push buttons. Each of those push buttons, a red, 3 green, an amber, and a blue, they are wired, connected in with the 6 toggle switches to give you the possibility of 4 state inputs: maintained on, maintained off, momentary on, momentary off. There's 6 inputs and 6 outputs there. Also on this particular training station you see some orange terminal blocks, white, and you see blue and green, then of course black, and you see some fuse blocks. The orange are for high-speed counters, the white are for pulse train output. Now this controller doesn't support 3 PTOs. And then the blue terminal blocks are additional inputs not connected up to the digital device simulator. That way you can connect up external things. And the same thing with the two green terminal blocks, those are external. And you see there's nothing connected up to them right now. I did not connect up the unused inputs and outputs of that 820 to that terminal block. It's there for future expansion. The system that I'm currently using is the largest one to the middle left, and that is an LC850. The 850 does come in a shorter version, a 24 QBB, amongst other electrical interfaces. I prefer the QBB because that's the one that supports pulse width modulation and pulse train output. If it's going to support it, it'll be the QBB. This is a LC50 48 QBB. So the 48 QB is the only one that supports 3 axes of motion. So that's why I focus my attention on this one, the one that takes up the most presence in the picture there. And you see down in front, I have more than 6 inputs, blue, connected to my digital field device simulator. In other words, there are terminal blocks there for 10, but I'm only using 6. Then from the green, you see 6 green wires going down to the digital field device simulator. To power this, you can't see it, but on the edge away from you on the digital field device simulator is a DC bulkhead connector that you plug in a 24 volt DC power adapter to. And from this digital field device simulator, I feed 24 volts DC through the red terminal block up to the outputs on the processor, the controller, and to the controller itself for power. So this is the hardware that I'm using. When I told you I own all of the Micro800s with exception of the 30, simply because I don't care for the 830, what I have here really covers all the bases. And actually I think that the LC20 with the HMI over there in the upper right corner is the most bang for the buck, but does not support a lot in the way of motion control. The largest one to the middle left, the 850, I think has the most flexibility for training purposes. Now, just so you're not totally distracted by the background, this is in my office, and I've just set these up on a little R&D layout. It's an N-scale model train, if you like, layout. I have the track, and by the way, this is DCC with sound. Direct Command Control basically treats the 2 rails as 2 conductors, but not in the tradition of the DC sense where you increase the voltage if the train goes faster, decrease it, slows down. If you want to reverse it, flips the voltage. The power applied to these rails is basically frequency modulated voltage. So it's AC, but it's frequency modulated. It's not 60 hertz. Embedded in this frequency modulation are packets of information, and each locomotive or each DCC encoder, decoder, it could be in a car to control lights in the car, it could be the engine to control speed, sound, and everything else. Each one of those has an address. And the packet of information that goes out on these 2 rails, there's a steady state, which is just AC, and then it varies in frequency to produce a binary message that begins with a decoder address and then the commands. You can have any number of devices running on the same track, and they're all individually controlled by a device not on the track. Also, you'll notice that there are some numbers here and there, like you see 8, 9, and up at the top you see 11, 12. There are a dozen isolated sections of track. Now the track has a common rail, but the other rail is isolated into 12 sections, and each of these sections has a wire conductor that comes back through a current sensor and back to the main power booster or command station. The device in between that senses the current provides a signal to tell the computer where the device is at on the track. My goal here is total automation. I don't run these with the little handheld cab or throttle. Rather than have you get totally distracted wondering what the toys are, they are toys. And this is in my office. And if I get bored working on the stuff that you're watching, the manuals you're using, then I go over and play with this. So right above this little 2x4 platform, I have a 40-inch high-def TV that is also connected to a tower that runs the railroad modeling software. So when I'm running this, and I have it on my iPad too, so I can bring up the iPad and control all of this. It's the automation of it that I am interested in, not what you would call traditional model railroading. Okay, these data types are not all of them what you have seen in the past. A Boolean is true or false, it's a 1 or a 0. But there are no individual physically isolated bits in memory. The native data type for a particular controller processor is going to be either integer, 16-bit, or double integer dense. So you see there, Boolean, single integer, integer, and dense. Typically, most modern processors have memory arrays that are made up of 32-bit words or double integers. Double because an integer right above it is a 16-bit. Typically it's signed integer, meaning you see integers from minus 32768 to 32767. That is because bit 15, remember 16 bits, that's 0 through 15. The 15th bit or the 16th bit, bit 15, is the sign. If it's 1, it's a negative number. If it's 0, it's a positive number. So signed integer does not give you 16-bit integer. A 16-bit integer would be 0 to 65,530 something. That's not typically what you get. A single integer is 8 bits, also called an octet, and if it's signed integer, then it's minus 128 up to plus 127. If it's not signed, then it's 0 to 255, which is what you're probably more familiar with. A long integer is twice a dent, so it's 64 bits, and that gives you signed integers from minus, I can't tell you what that says, to plus, I can't tell you what that says. Then there are what they call real, and real are floating values. So typically in the past you call them floating, and that means that it has a decimal point. Now this is single precision. So 1 sign bit plus 23 mantissa bits and 8 exponent bits. Then there's long real, which is 64-bit floating values, double precision, and that gives you 1 sign bit, 52 mantissa bits, and 11 exponent bits. So those are they call these atomic data types, Rockwell does, because all defined data types, like user-defined, predefined, they are made up of these data types. Okay, we also have byte, which a byte is an 8-bit unsigned integer. Instead of being a signed integer plus 128, or I'm sorry, minus 128 to plus 127, the 8th bit, or bit 7, is not a sign. It's part of the value. And then there's unsigned short integer, or byte, which would be 8 bits, but all 8 bits are dedicated to the value, then unsigned integer, unsigned dent, and unsigned long integer. Also, and these are some of these variables or data types you don't have available in the older platforms. We're talking about the Micro800. So there are data types like date data type that is specifically of a shape to hold a date. And then there are string data types, and each string data type is limited to 252 characters. And then there are time. So you have date data types and time data types. They are specifically predefined data types that can store the date or the time. And then there are also string. But string was available in the older platforms. You have arrays. An array is not really a data type, but you can create an array of a data type. For instance, with the older platforms in RS Logix, B3:0 was a 16-bit integer with the name B3:0. B is the data type, 3 is the file number, the colon is the delimiter, and 0 is the first word. But you could expand that file, B3, out to a maximum of 256 elements, B30 through B3255. You started with a single element array. Now there's no difference between an integer and a single element array as far as how you use it, only that you can expand it and maintain the nomenclature all the way through all of the elements. You can also work with structures. Structures combine different data types to create structured data types. And I think I already described one of those, like a timer, counter, control, etc.